Hi, thanks for watching. Shall we get right to it then? I want to walk you through CAMI, which stands for Cosmic Acceleration Minimum from Inertia. CAMI lives inside Kerr Torsion Cosmology, or KT. KT is Einstein's gravity with torsion included, the tiny twist in spacetime sourced by the intrinsic spin of matter. In the KT picture, the universe does not start from a true singularity, it bounces. A conserved spin density from that early era survives to late times. We call that constant sigma naught. CAMI is the late time piece of the story. It says there is a universal flaw under gravitational acceleration, set by inertia once torsion is accounted for. Here is the core of it. If you include spin and torsion, there is an effective inertial term that becomes important only when accelerations are extremely small. That term sets a minimum acceleration scale we call g sigma. Spoken out loud, the relation is g sigma equals alpha times h bar squared divided by m squared c cubed times sigma naught. You do not need to love the symbols to get the punchline. When you plug in the numbers, you get about 10 to the minus 10 meters per second squared. That is the level where rotation curves of spiral galaxies flatten and where the famous radial acceleration relation bends away from the simple Newtonian slope. CAMI says that is not a coincidence. It is the geometry talking. Think of it like this. Gravity fades with distance as usual, but in the ultra-gentle regime, spacetime has a built-in resistance to letting accelerations keep dropping. You can dilute gravity by spreading matter out, yet as you approach g sigma, the fall-off stalls. In the outer parts of galaxies, the system settles on that floor and the orbital speeds level out. No dials to tune, no galaxy-by-galaxy knobs. One constant, one floor. Quite sensible once you see it. Now the tests, and how they fared. We confronted CAMI with large public rotation curve catalogues across thousands of radii. The radial acceleration relation, which compares observed centripetal acceleration to the baryonic prediction, shows the expected high acceleration one-to-one line and then bends cleanly toward a common floor at about 10 to the minus 10. Low surface brightness dwarfs, ultra-diffuse disks, gas-rich rising curves, and high surface brightness spirals all approach the same floor within their errors. The baryonic Tully-Fisher relation drops out naturally, with a near fourth power slope and a 0 point set by g sigma, matching the observed band without extra fitting. Splits by inclination, surface brightness, stellar mass, gas fraction, and star formation rate do not shift the floor in a meaningful way. We looked for counterexamples. Systems that sit stably below the floor across multiple radii with clean systematics, and we did not find a persuasive one. The model is falsifiable, though. A single well-measured, equilibrium galaxy that holds a sustained acceleration below g sigma would rule it out. That is the kill box. Upcoming deep HI mapping of very extended disks and sharper outer disk kinematics are exactly the places to push. No faffing about, just a proper try at breaking it. Since you asked about tensions, here is what CAMI may explain and where lambda struggles. Lambda CDM is superb on the cosmic microwave background and large-scale structure. On galaxy scales, it often needs many moving parts. First, the tightness and 0 point of the radial acceleration relation are difficult to recover from dark halo assembly alone. Halo concentration, feedback history, and baryon fraction should inject more scatter than we actually see. In CAMI, the bend and its intercept are fixed once sigma naught is fixed, so the small intrinsic scatter is natural. Second, the baryonic Tully-Fisher slope near 4 with very low scatter is expected if there is a universal g sigma, while in halo models, the naive scaling prefers closer to 3, unless feedback and selection reshape the trend, and even then the 0 point must be tuned. Third, the cusp core problem persists. Cold dark matter halos like to form steep inner cusps. Many disks and dwarfs prefer cores. Feedback can flatten cusps in some cases, but it must be adjusted differently for each object. In CAMI, the inner slope is not forced by a cuspy halo, and the transition toward the floor happens where the local acceleration crosses g sigma. Fourth, the diversity problem shows very different rotation curve shapes at the same maximum speed. In lambda CDM, you need detailed star formation and feedback histories to explain the spread. With an inertial floor, much of that spread compresses once you view the data in acceleration space relative to g sigma. Fifth, The too big to fail issue highlights satellites that are less dense than the most massive subhalos in simulations. Baryonic fixes are possible, but again, they are case by case. With a universal flaw, the outer satellite dynamics are bounded by the same scale that bounds big disks. Sixth, the disk halo conspiracy that keeps total curves flat across a wide radial range is a feature in CAMI. The sum looks tuned in lambda CDM because two unrelated components must cancel slopes. In CAMI, the flattening is a geometric response to entering the low acceleration regime. And finally, on the particle front, after decades of exquisitely sensitive searches, there is still no laboratory detection of a dark matter particle. That does not prove it does not exist, but it rather raises the stakes on clean alternatives that make sharp predictions with fewer ingredients. CAMI is exactly that sort of target. If the flaw is real, the small-scale tensions above are symptoms of a deeper geometric constraint. If the flaw breaks, CAMI is out, and the standard picture stands. Fair play. Now let's tie this back to the bigger picture. KT is a one-constant framework. Sigma naught is fixed once by early universe physics. Upstream, it shows up in CHAD, which explains why the sky is so smooth, by giving you exponential damping of primordial vorticity, with a damping constant gamma equal to kappa times sigma naught squared over h naught squared. Downstream, the same sigma naught sets g sigma in CAMI, which explains why galaxies refuse to drop below the same tiny acceleration. You do not adjust the constant between these regimes. You carry it from the bounce to the present and compare to data in very different arenas. It also matters that the maths behind the framework has been hardened. The same analytic machinery that let us resolve the Navier-Stokes global regularity and the Yang-Mills mass gap problems is the backbone of how we handle geometry and invariance here. Those results tighten the barriers and help ensure the constants are well posed and the limits commute, so the classical predictions you use in KT are not built on sand. Rather elegant, if you will. So that is CAMI, the cosmic acceleration minimum from inertia. One simple flaw, one conserved constant, and a stack of observational checks that either confirm it or kill it. If you want the details, the figures, and the full pipeline, click the link to the paper on Zenodo. We would love your feedback, your pushback, and your ideas for sharper tests. Let us see how hard this flaw really is. Cheers!